So I do have to chop these into smaller files because the files are just huge and take a long time, especially here at home, to upload to save as both to save as videos and to upload them to the internet. Both very time-consuming things, so I'm trying to make these somewhat shorter or smaller files. So we're going to continue talking about the cutaneous senses as we get to our receptive fields and our thresholds and how we perceive details. I just include this picture because I find it fascinating. This was research done back in 1968 looking at absolute thresholds, so just detecting a stimulus, and we can see that the thresholds are slightly higher for males than females. Females are slightly more sensitive, and that we have lower thresholds for places like the nose, the back, and the belly, and higher thresholds, so we're less sensitive at the sole of the foot and at the calf and at the index finger for just detection of a stimulus. When we look at the cortical maps of the body, there is research showing experience-dependent plasticity. This research was done, this particular study was done by William Jenkins and Michael Merzenich back in 1987. If we look at the monkey's hand there in B, so what they are doing is stimulating that finger and measuring brain activity before and after training. So they're going to train the monkey on a task where they have to use their sense of touch in that finger in order to succeed at the task. Okay, so before training, as they stimulate that tip of the finger, we can see up in A, the activity of the brain is this little area of 2 there, representing that second finger. After training, they go in and stimulate that same little area of the finger, and you can see that there's in C, in the figure C, that there is more of the brain, there's more of the brain that's active in response to stimulating that finger. Okay, so again, experience-dependent plasticity, a change in the brain and its representation of the body based on experience. We have seen this for other senses, we've seen it for vision, we've seen it for hearing. I like to include this picture when I start talking about perceiving details, and I usually have people just ask you, and so think about this, have you ever tried to read Braille? So when I was a kid, I was legally blind by the time I was 6 years old, definitely. They found it, and I was already at such a state where they said she's probably been legally blind for a few years. So I really did not see well. And every time we went to the eye doctor, my mother would cry because my eyes would be so much worse every time we went. And so that scared me. And so she kept kind of, with her own fears, telling me that one day they weren't going to have glasses for how bad my eyes might get, as this fear of hers. And so I grew up pretty afraid that I might not be able to see one day. And so I used to practice turning off the lights or closing my eyes and walking around. And I also used to just try to read Braille. Well, reading Braille takes a lot of practice, and you're really only going to do it if you are in fact blind. And what we see with people who are reading Braille is that visual cortex, they're not getting stimulation to the visual cortex because they are blind, and that reading Braille actually activates the visual cortex. But I do want to suggest that you go to the elevator or wherever where you can feel the Braille. It is really, really impossible to feel the difference between, say, B and K or something like that, or C and E. That's really hard and for a sighted person to read Braille. When we start to talk about perceiving details, one thing that's important is measuring tactile acuity, and what we really want to know is how, so now it's not just detecting some stimulus, but how much detail can we get from a stimulus. And they do this in a number of ways. One is a 2-point threshold, so where we have 2 toothpicks or something, and actually this touch is one of the talks and times when I start doing a lot of in-class activities that we're not going to be able to do, but if you want to do this with someone, it really would help. This is a time, again, when I pair up students and get you to get 2 toothpicks and do this minimum separation on the fingers before you can finally see, oh yes, I can tell that those are 2 separate points and they don't just feel like 1 point somewhere in the middle, and to do that on the arm. So the 2-point threshold, what's the minimum separation between 2 points on the skin where we can feel or perceive that these are 2 separate points. Another thing they do is grading acuity. So just like we saw the gradings with the visual information, and we're saying which orientation can we see, they do this with little gratings where you might feel this with your finger, and what's the narrowest spacing of a grating where we can still judge the orientation of that grating. Another thing they use is raised patterns, often something like a letter or something. I'm not sure if we're going to do this e-reserve article where sometimes we do an e-reserve article where they feel raised letters with their tongue and talk about the tactile acuity of the tongue. But so they'll have some kind of raised pattern, not always letters, but some kind of raised pattern. And how small can we make that where you can still identify the pattern or the letter? So we're going to talk about some of these mechanoreceptors as we were perceiving details, and it really looks like it's the Merkel receptors that are telling us about details, and how one way we can examine this is with patterns. So there's these raised patterns, and you can see the bar along the bottom has a particular pattern where there are some little raised areas really close together, and then they spread out a bit. Okay, and then there are other areas that are raised that are longer. And what we see is as a person is feeling that longer area, the Merkel receptor is not really responding. As we're getting those little ridges in there, the Merkel receptor is responding, and if the ridge is more pronounced, so there's not another ridge right next to it, the Merkel receptor really responds. So I'm moving from left to right along the bar, and as we get more pronounced and separated, the Merkel receptor responds more strongly, and when we get into a blank space where there's no change, the Merkel receptor really is not, in that area, is not responding. So that's telling me that pattern is influencing the firing of the Merkel receptors. If we look at the Pacinian corpuscles and we are measuring their activity to that same pattern, you can see that the Pacinian corpuscles are responding the same regardless, pretty much, of where we are on that pattern. So they're not really giving us, and this is a person just having this pushed against their hand, pushing their hand against this. So if we're keeping our hand still, those Pacinian corpuscles are not responding. And we're going to see with our receptor mechanisms, we have better acuity in different areas of our body, really in our fingertips and our tongue and so forth. And better acuity is associated with a number of things. Okay, so I'm going to go through a number of things that influence how sensitive we are, how acute our sensitivity is. One is less spacing between the Merkel receptors. And so if we're moving along the y-axis, we're looking at tactile acuity, and remember, as my threshold's going down, my sensitivity is going up. So as I'm feeling with my fingertip, I have a lot of acuity. As I feel with the base of the finger, I have less acuity. And as I feel with my palm, I have even less acuity. And along the x-axis is showing the spacing, the spacing between those Merkel receptors. And in the fingertip, they are much closer together. And as we move to the base of the finger, they're farther apart, and they're even farther apart in the palm. So we can see this direct relationship between acuity and the spacing of the Merkel receptors. But there's more. I have another figure that shows some absolute thresholds, except instead of for detection, these absolute thresholds are for the 2-point thresholds. So moving the toothpicks apart, or whatever, 2 little things that are sticking the person, moving those apart and seeing when do I finally feel, yes, there are indeed 2, and it doesn't just feel like 1. Okay, and I just think that these figures are fascinating. And again, remember, sensitivity is low on the figure. So they're measuring thresholds. So those ones on the face and on the hands that are really low, that's where we have the most sensitivity, the lowest thresholds. Okay, so there's more to this better acuity. It's not just the spacing between the Merkel receptors being closer, giving us better acuity. We also have cortical mechanisms, so the receptive fields of those neurons in the cortex, where the area on the skin, that when we stimulate that area on the skin, it's going to influence the firing rate of a particular neuron, and we're going to see smaller receptive fields, right, when we are going to give us better acuity, just like we saw with vision. Those neurons that are responding to less information, and so have that more direct wiring like the cones, they're going to have better acuity. They're going to give us detailed information. So if we look at our receptive fields on our fingers, you can see that those are really small. And we're going to move out to our hand. They get larger and they are overlapping. This is exactly what we saw from going from the cones in A to the rods in B, or really maybe the cones in the periphery in B, and then the rods in C. If we move out to the arm, the receptive fields are even larger and there's even more overlap. And so if we look at how that translates into brain activity, and so we have those 2 points, I'm looking at a 2-point threshold, because if I have my 2 points that are pointing there to the hand are 2 different receptive fields, and they're hitting 2 different receptive fields. And if you notice in those little circles, there are receptive fields there that are between those 2 points. And so that activity is going to bear out in the cortex, right? Where we can see, if we look at the activity of the 2 points on the finger and read that, where those areas that are stimulated by those 2 points are going to be separated in the cortex because of the receptive fields. And if we look at the arm with those overlapping receptive fields, and we have those 2 points, and so he has 2 points pointing to the arm in C, and those 2 points are the same distance as the 2 points that are hitting the finger, but now those are in those overlapping receptive fields. And so if we look at how that gets translated at the level of feeling this in the brain, people are going to feel that as 1 point somewhere in the center of that, because there are no receptive fields in between, separated receptive fields in between those, that we can separate those in the brain. So the other thing that's also influencing and is related to those receptive fields being smaller for the fingers and larger in the arms is that we have more cortical space for that's representing the fingers, and we have less cortical space that's representing the arms with those overlapping large receptive fields. And again, this is what we saw with vision, right? That we had the fovea had cortical magnification. We had linear wiring and small receptive fields, and we got to the brain and we had more cortical space dedicated to the fovea. All of those things together gave us the detailed vision where we're moving our eyes around the world. Well, all of this together is giving us more detailed information from our fingers, from our lips, from our tongue than other areas of our body, where the receptive fields are larger and overlapping, and we have less cortical space devoted. So we've talked about perceiving details. We're actually going to get back to perceiving details, but we're going to take this break to talk about vibrations, because that's important actually for perceiving details as well, in a really different way. So the Pacinian corpuscles are how we feel vibrations. If you remember me going through the mechanoreceptors and talking about the Pacinian corpuscles as giving me the feeling of my refrigerator running, or the feeling my car running, or whatever, or my key going brrr, brrr, that those vibrations are felt by the Pacinian corpuscles. And how we know how Pacinian corpuscles work comes from work from Werner Lowenstein back in 1960, where if we look at A, if they gave a rapid vibration, we see that the nerve ending, if you can see the bare nerve ending, it is surrounded by what looks kind of like an onion, but what's in that onion-looking thing is a liquid. And so sometimes I compare this to a waterbed. If you feel vibration on a waterbed, you're going to keep feeling that. Well, that's what's happening when we feel a vibration. That liquid keeps moving and vibrating, and so that bare nerve ending is what's sensing that. Okay. So it's going to keep responding. If we have continuous pressure, just like if someone gets on your waterbed and they sit down, you're going to feel it when they sit down, but then it's going to stop, right? You're not going to feel it anymore. And so continuous pressure, if you look, we don't feel that at the bare nerve ending. We only feel it when it starts and when it stops. So when it comes on and when it goes off. And so what Lowenstein did was he pushed at A and noticed that this what the Pacinian corpuscles nerve fiber there, it responded when we started the push and when the push came off. And then he dissected this and kind of took off that surrounding area and went in and pushed at B. So pushed directly at, or stimulated directly at that nerve ending, and it responded constantly to the stimulation at B. So what it's doing is it is responding to the stimulate when it is stimulated, but because of this kind of liquid around it, that it's being stimulated only when something starts and when something stops, just like when someone gets on and off your waterbed. If so, what it tells us about is vibration. And for the Pacinian corpuscles, specifically, fast vibrations. So part of telling the details of an object is, or perceiving the details of an object, is perceiving the texture of an object. And this is where we really use both, it looks like, our Merkel receptors and our Pacinian corpuscles. And it looks like we use two different cues. And so this has been referred to more recently as the duplex theory of texture perception. And Mark Hollins has done a great deal of work on this with several colleagues. But this duplex theory of texture perception, really the crux of the theory, was proposed back in 1925 by David Katz, who suggested that we use spatial cues, so those relatively large surface elements, those bumps or grooves that we feel when the skin is moved across the surface, but also when it's pressed on to elements. Okay, so when I'm pressing something onto the skin, when we saw that weird raised pattern back and we looked at the Merkel receptors, those were spatial cues, right? As we're just feeling that pattern. Sometimes what I do is I pull out a notebook, and so you might want to do that with one of your notebooks. As you feel the top of the notebook, you can feel the entire thing, the pattern of it's just smooth, right? But if you turn your notebook so that you're feeling the wire edges, you can feel how close, to some extent, how close together those wire edges are. And now you can also feel that it's not smooth, right? Those are jagged kind of edges. So we're using those spatial cues, the bumps and grooves, but we're also using what he called temporal cues. So cues that we're using really across time, or the information about the specific vibration due to movement over the surface. And so now if you're going to take your notebook again and you want to feel across the top, there's not really much about a change over time. You're not really getting information that's changing for that temporal cue, and so you can tell that it's smooth. But if you go back to your wire, that wire binding, and move across that, you can feel again how, and you can do this with different notebooks that have different wire binding. You can start to feel based on the vibration how close together those wires are, and that it's not smooth, it's bumpy. So you're getting both of those pieces of information to tell you about the texture of an object. Okay, so for perceiving texture, this is a study by, I think it was Mark Hollins and Ryan Reisner, and they did some adaptation. So remember, we've talked about before the slowly adapting. When we are slowly adapting, what's happening there is neural fatigue, right? That's what we mean by the adaptation, as opposed to the rapidly adapting corpuscles here that are responding to on-off. That's really two different ways of talking about how these neurons are adapting, and it's a little bit confusing, but it is what it is. That's the way it's talked about. So if we look at what they were having people do in this study is participants were running their hands over a standard texture and a test texture, and people were indicating which texture was finer. Okay, which one had finer kind of grains of sand or whatever in this case, for example. And if you notice, so if I'm comparing two and I'm saying which is finer, if I'm at 50%, I am at chance. If I'm at 50% accuracy or 50% correct, I'm at chance level. And they had a number of adaptation conditions, one where there was no adaptation. They had the first adaptation condition where the skin was vibrated at 10 vibrations per second, or 10 hertz. They did this for 6 minutes, so fatiguing those neurons. And in this case, they're fatiguing the Meissner corpuscles. So if you remember, the Meissner corpuscles are responding to something like hand grip, but they are responding to those changes, those pretty slow changes. So these slow vibrations are going to fatigue the Meissner corpuscles. In the second adaptation condition, the skin was vibrated at 250 hertz. So this more like a vibration, like a hand vibrator or your car running or something like that. And so in this case, they are fatiguing the Pacinian corpuscles. Okay, if we look at the results, so looking at the figure, if there was no adaptation, people could tell the difference between those textures. They were about a little bit over 75% accurate. If we look at the adaptation of the Meissner corpuscle, so RA1 eliminated is how that is denoted there. So sometimes Meissner corpuscles are rapidly adapting 1. Pacinian corpuscles are talked about as rapidly adapting 2. It's just their other name. So RA1 is eliminating the Meissner corpuscles or fatiguing the Meissner corpuscles, and people are just as good at telling the difference between these two textures. And if we look at the second adaptation condition where the Pacinian corpuscles were eliminated or adapted, then we see now people are at chance. So it looks like really for us to tell the difference between those textures, we are using these, what we were going to call temporal cues, or the vibrations, so that what's changing over time. And if we don't have the Pacinian corpuscles, we can't do it. It's the Pacinian corpuscles that are allowing us to feel that texture. Research on temporal cues has also found that we can sense vibrations using a tool. So if you think about running a pen over the back of your notebook, and we can sense a surface remotely by the vibrations that we feel in that tool. And basically what we're feeling, right, is the tool vibrating, and we interpret that in our brains as texture.